This is section 11.3, areas of trapezoids. So we've already seen the formulas for the areas of a square, a rectangle, a parallelogram, a triangle, and a rhombus. Now how about a trapezoid? Remember, trapezoids are not parallelograms, so the formula for parallelograms will not apply here. First, we need a couple of definitions. An altitude of a trapezoid is any segment perpendicular to a line containing a base of the trapezoid from a point on the opposite base. So a segment from one base to a line that contains the other base. Since the bases are parallel, all altitudes will have the same length, and we call that length the height of the trapezoid. So for example, in this trapezoid, those are the two parallel sides, so those are the bases. Those are the two legs, they're the non-parallel sides, and they're clearly not congruent here, so it's not an isosceles trapezoid. One example of an altitude would be that one. It's from a point on one base perpendicular to a line that contains the other base. This time it would actually be perpendicular to the other base itself. But I could draw an altitude from this point, or any point over here, to the other base. Since it has to be perpendicular, it's going to have to go straight up like that, which means I'm going to have to extend the top base over there. So that would be perpendicular to a line that contains the base on the top of the trapezoid. So it may not be perpendicular to the actual base as long as it's perpendicular to a line that contains the base. But this means that no matter which altitude I draw, they're all going to be the same length. And we'll call that length the height, h. Okay, and that height is going to play a role in the area of a trapezoid. So let's try to derive a formula for the area of a trapezoid. Let's figure it out from what we know. The way I'm going to do that is, well, first let's say this is base 1 of my trapezoid. This is base 2, B1 and B2. And let's draw in a height. So I'll draw one there, and that's going to be h. Okay? Well, I could also draw in a diagonal of this trapezoid. The advantage of drawing that diagonal, imagine it's a nice straight line. Fine, I'll make it nice and straight for you. The reason I want to draw this diagonal is so that I break up my trapezoid into two triangles. This one I'll color in yellow. And then this one I'll color in pink. These two triangles are non-overlapping. So by the area addition postulate, I can add them together and get the area of the whole thing. So let's call this yellow one area 1, and call the pink one area 2 in Roman numerals. The area of the trapezoid is going to be equal to area 1 plus area 2. So the yellow plus the pink. If I add them together, I'll get the whole trapezoid, right? Well, I've got a height drawn for the yellow triangle. Let me draw a height and altitude for the pink triangle. So I'll maybe pick this vertex over here, and I'll draw it up there. I'll have to extend this top side, and then I've got an altitude. But that's going to be the same as h. It's still going to be h. Because those two lines are parallel, so they have to be the same distance apart no matter where I draw my perpendicular lines. So area 1, the yellow area, is going to be, it's a triangle, so we know the formula is 1/2 the base times the height. So 1/2 of B1, it's the base of the yellow triangle, times h, the height of the yellow triangle, plus the area of the pink triangle is going to be 1/2 the base times the height. Well, the height, so the base of the pink triangle is B2, and the height that I drew to that base is still h. Okay? Notice there's an h in both of these. So this was the yellow triangle. This is the pink triangle. There's an h in both of them. So I can factor that h out. There's also a 1/2 in both of them. So I can bring that out. And I'm going to use the distributive property kind of in reverse. And I'm going to factor out the 1/2 h from both terms, leaving me with b1 in the first term and b2 in the second term. So that if I were to take this line that I just wrote at the bottom there and distribute the 1/2 h into the parentheses, I'll end up with what I had in the line above it. If I'm doing the distributive property, it just looks like it's in reverse. And that right there is the formula for the area of a trapezoid. 1/2 times the height of the trapezoid times the sum of the bases. And that's what this theorem says. The area of a trapezoid equals half the product of the height and the sum of the bases. Half the product of the height and the two bases added together. We have to add those two together first, then multiply by the height and by 1/2 because of the bases, the sum of the bases in parentheses. So here's two examples, and we'll use that formula. Find the area of a trapezoid with height 7 and bases 12 and 8. Okay? So I will apply my formula, 1/2 height times b1 plus b2. Well, the height is 7, 1/2 of 7 times the sum of the bases, 12 plus 8. I don't even have to draw my trapezoid because I know what the bases are, I know what the height is, I can just plug them into the formula. Which means I'll have 1/2 of 7 times, what's 12 plus 8? That's 20. So that means I'll have 1/2 of 140. Half of 140 is 70. And that'll be the area of that trapezoid, just by applying the formula. Number 2. Find the area of an isosceles trapezoid with legs of 5 and bases of 6 and 8. This time I will draw it so you can remember what an isosceles trapezoid means. It means the two legs are equal. So if there are 5, that means both the left and the right there are 5. And the top is 6 and the bottom is 10. The bases are 6 and 10. So the shorter one is 6, the larger one is 10. I want to find the area of this trapezoid. Notice I don't have the height. I'm not given the height, so I need to draw it. Say I draw it there. That's h. But I could also draw it over here. And that's h. The advantage of drawing it twice is that I know this length is 6 because I've made a rectangle in the middle there. If the whole thing was 10, that means that the pieces on the sides split evenly 4, so that the 4 and 6 makes 10. So that's 2 and that's 2. So that 2 plus 6 plus 2 makes the whole 10. So then I've got two right triangles, and let's just take a look at one of them because we need to find what h is. So I've just redrawn this right triangle over here, and let's find h. How do I do that? Use the Pythagorean Theorem. So h squared plus 2 squared is going to be 5 squared. That means h squared plus 4 is going to be 25. So h squared is going to be 21. And h is going to be the square root of 21. Can I simplify the square root of 21? No, it's already simplified. Okay, so now I know the height because I found this, and it's square root of 21. I know the height, I know the bases, so now I can apply the formula. And the area is 1/2 the height times the two bases added together. That's 1/2 of the square root of 21 times, in parentheses, 6 plus 10. Which equals 1/2 of the square root of 21 times 16. Now all of these are multiplied, so I can multiply the 1/2 and the 16 together even though they're not next to each other. And 1/2 of 16 is 8. So this is the same as 8 times the square root of 21. And that is simplified. So that is my answer. So here are your immediate practice problems, which are exactly like the two examples I just did. Follow the same process I used. Number 1, find the area of a trapezoid with height 11 and bases 8 and 12. Just apply the formula, plug everything in. Number 2, find the area of an isosceles trapezoid with legs of 8 and bases of 10 and 16. Do the same thing I did in my example of using the Pythagorean theorem on one of the triangles on the end. And that is the end of section 11.3.